first we're going to just start with the positive side right here. The silver, or I'm sorry, I drew this wrong. Okay, I changed that. Books actually, on most of the time, the way they do this is they put on the right side the positive cell and on the left side the negative side. So if we just go by our equation, you want to start with a positive one, and it just so happens that that is silver. So first let's calculate for silver. We know for silver E naught is equal to 0.799. So 0.799 volts minus, and this math is fairly trivial. We're going to put a 2 in here because we said we're going to move 2 electrons. And this is multiplied by the log of, and here is where it actually is important to start paying attention. The product is a solid, so that's not going to be included. We're just going to put a 1 there. The reactant, however, this ion, this is 0.3 molar. So we are going to take that into account. And it also happens that it has a coefficient, and it's 2. So the reactant's on the bottom. It is squared, and we're just going to put a 1 up there for the product. It's a solid. So I mentioned I just put the 2's in there for consistency. It really doesn't matter. You could cancel these out right here, and you would get the same answer. But for this half cell reaction, we're going to get E for the positive side is going to be 0.768 volts. Okay, let's keep going down. For the other side of the half cell, or the other side of the cell, the other half cell, we're going to look at the copper, and the standard potential for copper is 0.339 volts. So we have 0.339 volts minus that nice constant we're using, over 2. We're moving 2 electrons. Now it's time to pay attention again. 2 electrons, and over here there's no coefficient in front of the copper, and again it's a solid, it's standard potential, and we are going to have 0.1 molar concentration of copper, because remember this dissociates into 1 of copper and 2 of the nitrate. The nitrate's just a spectator ion, so we're only going to focus on the copper. And so it's just going to be that over 0.1. So for our negative side, remember these are just assigned. The negative and the positive, they're just assigned because of where it is. It doesn't actually mean they are negative or positive, but we are going to get 0.309, and you'll see what I mean later. Okay. So that equation I drew again, or I drew up there, it is E plus minus E minus. So we had 0.768 volts for the silver side minus 0.309 volts for the copper side, and that gives us 0.59 volts. Okay. And that's a bit rounded, but I'm working off a paper I've got in front of me. So this is our standard, this is our actual potential for the cell. Now we're going to do one more thing to make sure that we're on the right track. We're going to calculate the equilibrium constant. And the equilibrium constant, it's a unitless measure of how much the reaction is going to go forward or backward. So we are going to take the number of moles of electrons times the potential for the cell divided by that nice constant we had earlier, since we're still working at a standard temperature. Or sorry, that's supposed to be a 10 there. It's equal to K. Sorry guys, I didn't have much sleep. 10 to the 2. Five, 9. And 0. And K gives us 3.3 times 10 to the 15th. And you might notice this is a really large positive number. And what this means is that it's going to be spontaneous. And also that it's going to drive forward. So if it was a small number, it would be less spontaneous and less apt to go forward. But most of the time when you're calculating these, if you get a positive voltage, you'll see this is what's going to happen. Okay, so that's all I've got for today. I'll try and do another electrochemistry video soon. And have a good one.